All right, and we will dive right in. And as I said, today's focus is on data review. So we have entered in the data into ARM, and we've confirmed with the different tools we talked about the other day, all of that data, and now we're really ready to think about analyzing it. We don't want to just dive into a report, yet we really want to take a look at the data in terms of the assumptions of AOV. And so we're going to start with a few slides that we did cover in our first session, just to review. So I'll go pretty quickly over them for anyone who already had to listen to me last time around. But basically, before we run the ANOVA analysis, there's some assumptions that we have to consider. And so we talked about the homogeneity of variance, and we actually saw that last time with the box whisker. Looking at the amount of variance for each treatment should be similar. They don't have to be identical, but you don't want a lot of variance in most treatments and then a couple of treatments with very little variance. You really want to have about the same amount. And we'll see some of the statistical tests today to really quantify what is an acceptable level of that difference in variance and what is not. The other big assumption of AOV that we have to deal with typically is that the data follows approximately normal distribution. And so that's your classic bell-shaped curve if you plot out all of the points in your data set. And so a variety of tools we have to look for that. These are all statistical tests that we'll see today, the skewness and kurtosis for how peaked or pointed and how skewed left or right the curve is. And then the Shapiro-Wilks will be a statistical test that just kind of covers the normal distribution as a whole that we will look at. Then we talked about a couple of other ones that are not as big of a focus. We don't have simple statistical tests that we can just throw out and take a look at. The independence of errors and additivity, using the heat map that we showed last time around can be helpful to spot some of those things. But really the first two are really our big targets as we look today. And so we really cannot rely on the AOV analysis if we don't fit those assumptions. And so we really have to take care to make sure that the data is correct in that manner to be able to use the AOV. And so we'll see today, we have data correction transformations that can be done with the data when appropriate that would allow us then to run the data through the AOV. There's also some spatial models. We won't dive too deep into that today, but we'll just kind of show where you can leverage some of that in the tools that we're showing. And then finally, nonparametric statistics, and we will show an example of that and how that fits in with everything too. So. All right, so with that, we will dive in. And I have a trial here. It's a little different from the example we were using last time. Just has more data columns, so just more examples to show you essentially. So here I am in the data editor, and we have, as I said, multiple assessments that have been recorded over the trial here. And so I'm just going to start in data column 1. And really, just about all of the data review steps really can all be performed with the column diagnostics panel. So this is usually hidden by default, but if you go all the way to the far right side of your screen in the data editor, you'll see at the very right, there is a column diagnostic pane here. It's very similar to the column properties we had looked at last session, but this one we want to open is the column diagnostics. And then I'm actually going to unpin my regular properties here, just so we have a little more space on my screen. And then I will extend this column diagnostics panel out. And we saw this for just a brief moment last session. And really, we have this diagnostics panel split into a couple of sections. And so this first table here you see is, I would casually call it the stats of the column, not necessarily statistics, but different information about the column. And we had looked at the first few rows here kind of as the data confirmation steps, just describing how many data points you have, how many unique values throughout that column, how many are analyzed as opposed to being missing or marked as damaged. If you're missing enough data where all of a sudden number of replicates are impacted for a given treatment, we can see that, or if an entire treatment is missing somehow. So that first section there, just kind of descriptive of the data column, again, that we are clicked into. And so I'm still clicked here into one. And so that's what we're looking at is the diagnostics there. So that's a great start, but really the focus is on these next 4 rows. And let me scroll down just one more line here, starting with the Levines. And you'd recognize these were all on our slide, the Levines, the Shapiro-Wilks, skewness, and kurtosis. So these are those tests that we can use to really look and decide if there are any issues with those assumptions of AOV. And so the Levines is the homogeneity of variance test. And here in the table, then what we are presenting is the p-value from that test. And so basically, it's the same thing for all 4 of these are statistical tests being run then. And so the p-value of the test, essentially, if that value is significant, which would be smaller number than your alpha level, typically 0.05. If it's smaller than that, the test is significant, and that means there is an issue for us to look into. So significant is bad in this case, or at least would mean that we need to do more because one of the assumptions is not met. That test is failing. And so the columns of this table, we have the raw data, that's just referring to the data values themselves. And we can run the test on those data values. This IID column is actually referring to the residuals. And so that's one difference that we brought in just in a historical context of ARM. Maybe 5 years ago or less. I think this tool has been around for 2 to 3 years now. But before the column diagnostics was introduced, most of the data review tools we had were looking just at the raw data. So the tests that were done were on the raw data. But the industry has been moving towards really testing these assumptions on the residuals of the data. In essence, really thinking of, real roughly, you're kind of referring to the error behind the scenes, in a sense, when we talk about these residuals. And so really with more computing power, these statistical tests makes more sense to run on the residuals. And so that's where we brought in the column diagnostics, is also bringing in that more modern approach to looking at the residuals. And so really here, this is really the decision making you would want to do, is these values, p-values here in this table in the IID column. That's what we want to use to decide whether or not we have an issue with the assumptions of AOV. And I do so we have a question. It's a nice suggestion as far as highlighting some of these values that are not valid or significant. And so that is a great suggestion. I think we had an idea to maybe put the text in red or something along those lines to bring out those that are failing, that are lower than your significant value. So that's a great suggestion we may be able to add in the future to kind of make those pop up. So looking at this particular data set, we can see that all of these p-values are not significant. And so that is good. That tells us that there are no departures from those assumptions, and we can proceed with the AOV analysis without any concern. And so one of the reasons this IID is here is we actually added that code, which is short for identically and independently distributed, is really to provide a way to mark that you've reviewed a column of data and did not find that any further action is needed. So if I click on the checkbox here next to IID, what ARM will do is add this code to the ARM action codes row. So this is a way to indicate that I have looked at this column, but there were no actions to take. So just a nice confirmation. Otherwise, if we just left it empty and moved on, then if somebody else came to look at this, do I still need to review this column? I'm not sure. So it's kind of a way to check it off that it's been looked at and there just wasn't any additional steps that we needed for that column. So that's another reason we added that kind of cryptic IID code there, really to provide that checkbox of sorts. Now, much like the other tools we saw in the data confirmation step, there's a next button in the corner that will help us move the cursor to the next column of data. Or of course, you can always click back and forth. If you see, I'll click, all the numbers will change. If I click back into column 2, the calculations will update. So whichever column of data you click into, the table will refresh. So if we take a look at this next column of data, I'm gonna again come back to our 4 tests here, and I can see in the IID column, the Levine's is failing. The rest of them are okay. And so with the Levine's failing, there actually are a few more columns that have joined us in this table, and you may recognize some of them, the AL, AS, and AR. These are potential actions we can take. And so those are suggestions. In this case, the AL is the automatic log transformation. AS is the square root transformation, and AR is the nonparametric. And we'll dive into that a little more later. But really, they're just tools in our toolbox that we potentially could use to correct the assumptions of AOV. And so we could kind of look at each of these numbers and say, okay, well, AL is going to help us with Levine's, but it makes Shapiro-Wilks a little sketchy. We could look at each and every one of these values as we go to try to figure out what's the best combination. Or if we go down to this next section in the column Diagnostics, we have a recommendations table. And really some automation, if you will, of that decision making we have in ARM. So ARM can actually suggest what would be the best action to take based on the results of those tests. So what we see in the recommendations table is a row for all 4 of those statistical tests that we want to use. And then we have a recommended code based on the results of that test. So if I hop down to like Shapiro-Wilks, we had saw there is not a significant test there. That is not significant, so we don't need to do anything. And therefore, the recommended code is IID. But for the Levine's, we do have a significant test. So there is some sort of action that should occur. And so in this case is suggesting the AL action, the automatic log. And there is a comment here to just kind of explain the thought process. If we do a transformation, that will stabilize the variance. And as we saw up here in the AL, then the test is no longer failing. So kind of choose your own adventure here. If you're kind of a math nut and you like to look at a bunch of, a table of numbers, you certainly can dive into that here. But as you get moving, if you want to review kind of quickly through this, my eye always starts going right towards the recommendations table and just looking at the list. And really, the order here is kind of our statisticians' thoughts on this, how significant each one is. So really, if there's a problem with the Levene's test, for sure you should deal with it. Shapiro-Wilks would be pretty indicative. If that one is failing, that something is wrong. But there may be some leeway as you get down here if there's only a little bit of kurtosis, that maybe it's not necessarily worth running a transformation. You have some leeway if you're statistically inclined and want to make that choice. But certainly it never hurts just to run with the recommendations. But I do want to show as part of this recommendations tool here is there's an option here called the basis. And that's really to direct ARM as to what is the most important thing to consider when looking at your toolbox of what to use. So for example, our list of transformations, the log, the square roots, the arcsine, a lot of times those have kind of particular uses. Particular types of data lend themselves to a different transformation. And so we can simply look at the assessment values. What were the values there? Look at the test and say, all right, whatever works will work. But we could have ARM look at the rating type, for example. And in this case, it is a count. And so count data lends itself more towards a square root transformation. So it's more common to use the square root transformation when you have counts, because looking at kind of the underlying distribution of the different types of data you would take is really where that comes from. And I think I outlined those real quickly in our overview in session number 1. But so if you recall, when we were just looking at the assessment values, when we first started here, the recommendation was AL. So ARM is only looking at the numbers in the column and say, hey, AL will fix the problem, so let's go with that. But I can give ARM a little more information and say, well, consider not just the numbers, but the fact that these numbers are actually counts of things. And now we have that logic built in that counts are tied to AS as a more typically used. And so if the AS action will resolve the test, which if we look up here, it will, then it will be the recommendation that we have. So you can do that. If we look at these options, it will look at the assessment values, just the raw values themselves. If you have an action code that might define a rating scale or something along those lines, we can point ARM in that direction. In this case, I don't have any, so there wouldn't be much more to learn there. And then as we mentioned, the rating type or the rating unit. So maybe your rating unit is a percentage, and that may give ARM a better idea of what these values are. So you can change that to really find that additional level of information and pick the best transformation for the data. So a couple of questions here before I get too far along. Thinking about the recommendations, and the question is, what's the best choice here for the basis? I think that I would look at both the rating type and the rating unit first, as it really provides a little more information potentially. Of course, it does depend on your rating type and unit itself, what you actually did. There might not be kind of a built-in logical link to a transformation. And in that case, if there isn't that extra level of information, then ARM kind of falls back to the assessment values. So yeah, I think if I were running it, I would start on rating type each time, but also in the back of my mind think, is that informative enough, or should I try it with the rating unit? That's a good way to do it. And if you're curious about kind of how technically that is done, if you've ever noticed in the rating type list, there's a column that's been added somewhat recently for family. And that's really where ARM is getting that brains, if you will, of logically understanding what's going on. So we went through all of the different rating types in the list, which is another great reason to make sure you're using the lists from ARM to describe your data. And then ARM can understand what you mean, that we're talking about count data in this case, as opposed to here, there's a percentage. And a lot of them are blank if there really isn't that logical link, but in this case, it's a proportion. So ARM will know that it's between 0 and 100, and there's probably a particular transformation that lends itself better for that. So that's where it's kind of utilizing that intelligence there for the rating type, and as well as the rating unit too. And looking at Levine's versus Bartlett's, so I believe in general, the general statistic, information that I've seen, I think Levine's in general is more preferred. If I pop open our print reports, you can select which one you want to use from the descriptive statistics. It's the homogeneity of variance test, and you can run Bartlett's. I believe that's what we had in ARM originally, and then Levine's was added, and I think that overall performs better. It's less sensitive to skewness and kurtosis, but still performs as pretty much as well as Bartlett's when you don't have any normality issues. But I think in some industries, in some cases, the Bartlett's is still desired, and so we of course leave it in. But when in doubt, I think Levine's is generally more accepted. And I had one more question here before I get too lower. It was a question on the residuals come from some type of regression. And I'll be honest, I don't have the statistical background to answer that fully. So all I really understand with the residuals, you're really looking at the error. And that's kind of what we're looking at behind the scenes in a sense. But I can certainly kind of run that past our statistician to see if he had any more details of what exactly that means. Is that some sort of regression, or how those are calculated? So that's a good question there that goes past my knowledge. So I might learn a little bit this morning as well. So thanks for that question. And let me just make sure I haven't missed. There is one other question referring to kind of the basis here about selecting the parameter made during the report. And so currently, really all of this analysis is really limited to this screen. I believe we have heard an idea of maybe somehow including some of this output in the reports, but we don't currently have that yet. I think if we do create a report that would include some of this information, we definitely would make sure that that basis option comes through, so you could select that. But as it stands right now, the diagnostics here is really a tool you would use and then make actions and selections, which you can see we end up saving in the ARM action codes field to provide instructions for the reporting. Not necessarily that all of this information maybe belongs in a report. So really right now it's limited to two on the screen, and have somebody knowledgeable wanting to make these decisions with this information presented to them. And then those decisions are saved into the action codes to instruct the analysis portion later on. Great questions. Thank you, guys. And this one here that just came in, I'll actually let that go for just 1 minute, and we'll cover it here as we select the action here. So we've really seen the two tables and the basis that we would utilize. And so now we have an action, a recommendation here from ARM that AS is what we would want to do. And so kind of like we had done before with the IID, we can certainly come up to AS and click this checkbox, or we could manually type in AS into the action code, or you can also double click on the row that you want to apply. So I'm going to double click on AS here, and it will add that AS action code to this column. And if you haven't used automatic transformations before, this means that when we do the analysis, ARM is going to transform this data column using the square root transformation in this case. And then on the data that's been transformed, we will run the AOV analysis. We'll do mean comparisons, etc. So again, the idea is that the AOV, we really can't rely on the AOV results if we aren't fitting those assumptions. And so doing an action like transforming the data, we're transforming all of the data points at the same time. So we're not changing any results, we're not fudging anything, but we are changing the distribution of the data so that way we can run the AOV analysis on it. So that's the logic behind there. And so then the question is, hopefully, kind of explain that with the automatic, that we aren't changing the data. We don't have a separate data column that has that transformation. It's all done internally in the report. There is an option, if you wished, instead of having it all done in one column, we could insert a data column if we would like. And then instead of doing an automatic square root on this column, we could tools transform and do a square root of column 2 and save that in column 3. And maybe I'll just give ourselves 4 decimals of accuracy. So now instead of the automatic square root, we will actually have the literal transformed values in this column. Oh, and now I keep touching things and it's offering to not recalculate my values, but that's fine. So now we literally have the transform values in this data column. And so our analysis will run on column number 2 and column number 3. And statistically, this is the column we care about. And I would say in general, this is a little bit messier. And I think I would just take a half a second to point out a relatively newer option we added kind of for that case. Because a lot of times I think what you're asking perhaps is really because you want the raw arithmetic mean on the report. So a lot of times, one side effect to the transformation is that then what do we display on the report? You end up with either the transform numbers, which we saw in this case, 8s and 7s and 3s. Your mean is going to be nothing like our counts are, and that would look strange and unusual in a lot of cases. So then a fix for that is to de-transform the means back into the original units. Well, that ends up being a weighted mean, and it isn't the actual mean of the raw data. And so a lot of times I think that's the motivation for taking that transformation and putting it in a new column, so that way this column 2 still has that raw mean, that arithmetic mean. And so really, I think it makes your reports messier and harder to read. And so we added an option, and you'll find it in the mean description section, where you can include the arithmetic mean. So now you can use the automatic transformation, put that in data column 2. You can have all of your statistics run the way we want to run them, being transformed, but you can still print out and provide that arithmetic mean that is the true mean, if you will. Some people would feel of that raw data. So that would be my recommendation. Exactly. So the comment here is that de-transformation slightly changes the original value, and that's why people want both columns. And so I would recommend instead to turn on the arithmetic mean. So maybe I'll do that just real quickly here, is we will delete this data column. Yes, we want to remove that and put the action code here. And then just real quick, let's generate the report with the arithmetic mean as well as the primary mean. And I think I can maybe even get away with previewing it here, because it should show us the second column. So if I just zoom in, and you can choose whether the arithmetic mean shows on the right or underneath. But in this case, it will have the de-transform mean. And this is, I would call it the statistical mean. That's what we used in the statistics to make the mean separation. And so in the statistic world, we care about that mean in some ways, that's the one we used in the analysis. But in the real world, if you will, we have the arithmetic mean, and that's the one people like to see. So you can see there's slight differences. That first row is the de-transformed mean, and then this is really the raw mean that you would want. And so you can see that there are slight differences in those because of those statistics and how that transformation is done. So this was the main reason we added this arithmetic mean option. So that way you don't need to don't need to double your trial size in the sense of how many more columns you have. And so that's really why we added that option, to be able to make that visible. And yeah, for registration, BADs, things like that, we were getting a lot of feedback. I think primarily in Europe, a lot of this was requested. So a lot of the registration bodies and the way reports are done in Europe, it's really important to have that raw data. That in this case, it's the arithmetic mean. You could also run, generate the assessment data summary to have that raw data there, to have that available. So that would be my recommendation. Again, I showed it real fast, but it's on your AOV means table options in the mean descriptions. You can show that arithmetic mean, and you can choose whether it's under or beside. I kind of actually like it beside. I feel like it's a little bit cleaner when it's beside the mean. There, so the de-transformed automatic square root is really what that is. So we're pointing to this column is your statistics. So we've got the statistical mean and the results, the mean comparison test. But here we have the nice simple explanation of your real world arithmetic mean. And if you did want to get rid of if you want just the arithmetic mean, you could always turn off the primary mean. that works too. If there really is causing problems to have that detransform mean, we did kind of also in that same change, changed it so that mean can be turned off. So you have the arithmetic mean, and then you have the statistics. But we wanted to make sure that it was clear that the statistics were generated on something other than the arithmetic means. Because if you were to, look at the LSD value and start to compare and say, well, that doesn't match, it could also have confusion on the other side, potentially, if you don't quite understand what's at play. So try to make the report as straightforward as possible. So great questions. I hope you'll at least give that a roll to try out that option, so that way to simplify trials, because yeah, it really just gets really unruly pretty quickly to suddenly have 50-70% more data columns in your trial just because of these transformations. So hopefully that'll help. All right, so the last tool I haven't quite shown yet on the diagnostics panel is these graphs here. So we've chosen our AS graph, but we could do this before or after our selection. We can generate, I'm going to do a 2x2, and this layout will make sense in a moment. We can generate diagnostic graphs to visualize some of these tests. And really, if you want a deeper dive into the statistics and making these selections, in this case, so this text here will tell you what graph you're going to generate based on the row that you're clicked into, or the column that you clicked into up here. Either one takes you to the same place. So here I want to investigate my AS. Is this the right selection? Let's go a little deeper to decide. And I will press show. And we are running R in the background, and R is going to generate some graphs for us. And it popped up on my other screen. So let me bring it over here. And so the 2x2 layout is just how many graphs do you want on a page. 4x2 squishes it all into a single sheet, but will make it pretty hard to read, especially here as I share my screen. So I went 2x2. And so what we have is on the left half of the page, we have the graphs. This is the AOV residuals. So this is before any transformation took place. What did the data look like? And so we have a box whisker, which, as we did last session, is a nice way to visualize the variance. And so you can see treatment 1 had a lot of variance, treatment 3 a moderate amount, and the rest of these had a pretty consistent amount, as we're just looking at the height of those boxes is really what we're doing there. And so then we can see the Levines did indeed end up as significant. We also have the normal QQ plot, and that kind of ties with the Shapiro-Wilks test. So we can reference that p-value we saw in the recommendations and take a look at the graph to see kind of how that lined up. And there's not really any significant issues there. If I go to page 2, following this same column, now we have a spread location to give us a sense of skewness. And then finally, the histogram, we can kind of visualize that kurtosis, really looking at the bell-shaped curve, and nothing really pops out here. If I go back to page 1, the other half of the page is the AS. So now, on the left half, it's before, the right half is after. So now with the AS, how are things? And so you can compare side by side what this action will do to the data and visualize that. So here now, we end up with more consistent variation. That p-value is now not significant. So we corrected things like we wanted to, and we can also verify that the Shapiro-Wilks maybe got a little slightly worse, but we're still above water on that. So that is just fine. Skewness and kurtosis as well. fine. In fact, kurtosis got even better. So a way to visualize, to go a little deeper if you want to on that information. So again, that was the graphs there for one of the proposed transformations. Just real quick, if you did want to see the IID graphs, what that provides, very, very similar setup. It's the same visualizations, but on the left is the raw data, and on the right is the residuals. And so just looking at the difference between those two, that's a way to visualize that. And again, we're really moving statistically, at least kind of as the industry is going to really caring about the results of the tests on the residuals, whereas before it was just looking at the raw data. So. And I mentioned this is generated in R. There is a button down here if you want to take all of this analysis and run it in R. You can actually save an R script. So if you're using RStudio or R itself, slightly different code there that will generate, but we will actually generate a file that you can open in either of those versions of R, and you can see exactly what we're doing. If you want to change it and do what you want to do with it, feel free. It's just a nice export to be transparent in what it is that we are doing in this analysis. And so to kind of address the question that, I guess this export is, the save to R is limited to just this analysis here on the column diagnostics. We are in general working on making some of that other stuff available for all the other statistics that get done in ARM to do something similar. And you'll notice we have both R and SAS. So if you are using SAS, it does kind of the same thing. It will generate the script per se for you to run in your SAS program. And our statistician actually has a real extensive library as we add new features and statistical tools in ARM. He does tons of validation against R and against SAS to make sure that we're calculating the same values. We're doing the same calculations as these other statistical programs. And so he's got tons of documentation and we have some of it out on our website in a published verification section. And we hope to kind of continue to expand that for those folks that want to get their hands dirty with that code, or even just kind of look to see, oh yeah, verify that, yeah, you're doing it exactly like I would do it, just to have that transparency of what ARM is doing. So feel free to use that R for this analysis here and see what's going on behind the scenes. So I'm just scanning up and down this tool here, and that is really the big hitters, the big pieces of information you want to use and tools on the screen that you can utilize. I do want to make sure to do an example of the non-parametric. So I'm going to scroll over. I know my column number 12 here has that. So of course, you would want to click into each data column as you go through to review each one. I'm going to cherry pick here down to 12, but definitely review each of your columns that you're able to. And just looking at 12 now, when you click here, as we saw, everything recalculates. And really the first thing that my eye jumps to is this code column. So, if you don't want to sit down and spend 5 hours on a single trial, popping up graphs and looking at all the numbers for every single one, the fast and dirty way to review this is really click in a column and look at your recommendations here. And you can see that while the Levine's is not failing the test, our Shapiro-Wilks is. And if we just look at this table to kind of demonstrate that, Shapiro-Wilks is significant in the IID column, and none of these transformations, the AL makes it worse, AS is worse, AA, none of them are fixing the issue. And this assessment is a lodging percent. And even if we wanted to, we could peek at the histogram to see exactly why there's really no hope for a bell-shaped curve. And so this is really indicative of this type of data where you're going to have a lot of zeros, and only every so often are you actually going to have the presence of the pest. And so that type of data is just not going to have a bell-shaped curve, just no matter what you do, essentially. And so whether it's just the way the numbers kind of end up, or kind of an inherent way that the type of data that you're working on is, sometimes it's just not possible in our toolbox of transformations to find one that will allow us to run AOV. And so that's where, previously, before we had this non-parametric statistics, we were kind of stuck. But now we have non-parametric statistics, and essentially that is, let's just forget about AOV entirely. That way we don't have to worry about the assumptions. And instead, the non-parametric analysis is done. And so that really looks at ranking the data. So it'll just line up the data points and rank them from highest to lowest, or lowest to highest. Doesn't really matter. And then we can get mean of the ranks. And then the nice thing is we can still do a mean comparison on those. So we can still do a lot of what we have as the end output, just the insides of how the analysis is done is different. And so that is done with this AR action code. And that's short for the automatic rank. It's kind of how we put that in there. So I'm going to double click on that to add this action code to column 12 to run the non-parametric statistics on this column. And so I just kind of want to show real quick. So I'm just going to open up my properties and create an AOV means table, just to show that although it's a different analysis, we're not running AOV anymore, we're generating the non-parametric statistics just for column 12. So all of the other columns that we looked at before will still have the regular analysis, but column 12, oh, and then we were messing with the means. So let me close this and go back. I'm off screen here, but I'm just switching back those options. So we do have the primary mean. Maybe I'll take off the arithmetic mean just for clarity's sake here. But we'll see that the same report can be run. We don't have to do anything different in order to analyze this data column, column 12. It's generating the report here. As I said, it's just really going to rank the data, and we can still have our mean comparisons and everything else that we're used to, really. Just knowing that in the background, things were done a little differently because we can't rely on the AOV. So let me find column number 12. And so here, kind of balance how small it is versus what I can fit on the screen. We will show for the mean, we will show the arithmetic mean, but then we'll make sure to put in the footnotes, there's this R, which tells us that the mean comparisons are based on the plot ranks. So similar to how we do a transformation, where we really want to run the statistics on the transformed data, that's what we're doing here. But the transformation in this case is that non-parametric ranking that we do. And so there is no standard deviation, no grand mean, CV. Those aren't in the analysis at all. We're not looking at means. We're not looking at standard error, things like that. The non-parametric statistics instead are run. And so that's really the difference there. And just one other note, we don't have all of the mean separation tests available for the non-parametric. So it will run either the LST or the Tukey's HST, just depending on what you have selected. And so we want to make that clear as well. So you may have another line here for the mean separation test. Everything else will be run based on your report options, but just to make it real clear that those non-parametric might have a slightly different test run on it. And so let me show here with the AR. I want to make sure I get my terms right. There's a question about what non-parametric test is actually being run. And ARM will choose the correct one based on your design. So it'll do either the Kruskal-Wallis, the Friedman's, or an aligned rank Kruskal-Wallis analysis, just depending on the experimental design. And ARM will choose that for you automatically. I think we put this in order. So Kruskal-Wallis is if you do a CRD, Friedman's is if you're doing RCB, the randomized complete block, and then the aligned rank Kruskal-Wallis is all of the other ones, if it's a multi-factor or a lattice, things like that. You certainly, if you did have a specific one you wanted to do, there's an override. You can choose a different action code instead of AR to do the aligned rank or the Kruskal-Wallis if you really needed that. And just a quick note in the question about having an R script for the final report, we don't have that yet. I know kind of bits and pieces Peter's working on having available, but I don't think we have that currently. Kind of the save to R for the final report. We don't have that currently. There's a lot of things that get pulled into it. And there was a question on the skewness graph when we were showing the graphs, kind of how to interpret that. And you may have noticed I skipped over some of the graphs more quickly than others because I don't have quite as good of experience with those either. But that's actually a future webinar we'd really like to run, have Peter, our statistician, come online with us and have him show us some examples and really talk through how to use those diagnostic graphs. So we'll be looking for that, working on with his schedule to see when he'd be able to join us. Maybe if we can schedule one this fall yet, we'll be able to bring that and go even deeper into those diagnostic graphs and see some great examples of what to look at in those graphs to really get a better understanding of the data there. So really great questions here. We're getting close to the end of our time, so I'm just checking my list to make sure I've covered everything. You know, one thing we've mentioned in the slides, and we don't have a lot of time to get into the nitty-gritty, is the spatial models. So just a quick point on those. If you want to utilize those, let me move to a column where I haven't already selected a code. You can turn on this checkbox, and essentially that will add spatial models to your toolbox. So there'll be more data columns over here for to have more spatial models, or I should say to bring the spatial models into the list of possible actions to take for a data column. The reason this is something you can turn on and off, really, as I understand it, the spatial model, if you go that route, you're really dropping out any blocking that you have done. So if you're running the RCB design, if you're running a spatial model, you're really foregoing any of that blocking and we're taking a different approach. And so in general, you would have more statistical power, better results if you leave the blocking as is, if the blocking was successful. And you can see that if you print the AOV table, the full AOV table, you can see your replicate, you know, the replicate effect. And if that turns out to not be significant, and really find out that the blocking didn't capture the variation like you wanted, in theory, your block would be fairly homogeneous, and then each replicate, each block across the trial then has its own separate similarity to it. If you find that didn't happen, there was some unknown gradient that really messed up the data, then the spatial models are tools to recover as much information as you can. So almost a last ditch approach, not something you would just probably want to blindly turn on for every single trial that you're looking at, but is a great tool for when you have a trial kind of in that dire situation where something just went crazy in the field or things didn't go as expected, to be able to utilize some of these tools. And you can see there's those suggestions that can be made. There's a few more statistics that are added to the table up and below for selecting which of the spatial models is most appropriate. So again, that might make a really great webinar in the future sometime as well to really dive into that further, but that's just really kind of the starter pack for the spatial models. Is don't use it blindly just because it's there. You really want to have a specific reason to use it, or maybe a great tool. If your statistician starts to talk about, maybe we should use that for this case. Say, hey, ARM has that, maybe we can look at it. And then the last thing I want to highlight is in the print reports. Those of you that have used ARM for years may recall that when you generate a report, the AOV means table, ARM can ask you about your data columns and say, we notice skewness in column 2 and kurtosis in column 4. Do you want to take these actions? And so that was kind of the old way of data review. Again, we kind of touched on it earlier, where the analysis, all of those tests were done on the raw data. And kind of the other beef I would have with that old system as well is if the data transformations didn't work, we didn't have any nonparametric statistics to fall back on. So really you were kind of stuck. Okay, these 3 transformations don't work. What do we do? No, not analyze this? Well, the only other suggestions were, well, what if we exclude the check? Because in some cases that's logical, but in a lot of cases it's not. So it could recommend tossing out a treatment or tossing out a replicate, which really is not great. Obviously, in a worst case situation, it could be done, but that's kind of one of the biggest grimaces that I have in seeing that tool is just that being an option, because really it would be the last ditch approach. And now there's so many other tools we have with the nonparametric and the spatial models that really there's more tools before you start throwing out chunks of data. And so I just kind of want to show real quick how to turn that off. So in your AOV means table options, it's in the general summary section. There is an option near the bottom. It might be one of our longest options text-wise in the software. Apply automatic transformations or treatment exclusions to data columns that violate assumptions of AOV. So that historically, by default, was set to prompt, and that is those questions you see when you generate a report. Now, I would highly recommend that now that you've seen the data, really the data review tools we have in the column diagnostics, set that option to no. And ARM won't ask, because that's the old logic. That logic there is not what we're using on the column diagnostics. So set that to no. ARM won't use that old routine for reviewing data. And instead, now you can come to the column diagnostics and review your data with all of these tools to use, instead of just a quick yes, no, and have a whole bunch of actions done without really looking and understanding the data. So hopefully that kind of helps with that question there about printing out the suggested transformations. I think you really want to turn those off because those suggestions that come up are not the same suggestions that we see in diagnostics. The primary difference is the difference between this raw column and the IID. So if you ever want to compare kind of before and after the way it was before now, that's essentially the difference. If you do see a difference in what's being suggested is that old prompting is looking at these numbers and saying what needs to be done. Oh, Levine's just failed. The Shapiro-Wilks is failing. Skewness is failing. So it would really think there's a lot of problems to have in this data column, whereas now looking at the residuals, it's actually just Levine's that has to be dealt with. So that's my soapbox here as we wrap up for the day. Just knowing that we kind of have hit our time limit here. But certainly I can stay on for some minutes if there's questions, and I see there's a couple in there, but I do want to be respectful of people's time. So if you do have to go, again, thank you for joining us today. We'll have one more session next Tuesday for the reporting, and we've kind of seen some of these options already. So we'll get to dive in again and get even more specific on some of the different options, common questions as you're generating your report. To really get the nice report. Now that we've reviewed our data, we're ready for all that analysis. And so thanks for those that might have to run. I am available though for questions, and I'll tackle some of these here. So feel free to keep firing questions if you have them. But thanks for those that might have to run. So looking at the questions here, I think we covered the suggestions with the printout. The adjusted mean in the report options, kind of tied to the reporting here. If I bring up the options, there's this adjusted mean. It's kind of related to the least square estimation, as it does a linear model. And so really that's kind of specific to if you have missing data. Inherently in this analysis method, if you have missing data, then the analysis will make adjustments to try to fill in that missing information in a sense. And so then that would be the adjusted mean. So if you're familiar with the traditional AOV, that absolutely needed even data. And so it ties in with your missing data estimate. So you would actually have to have a literal data estimate. You could use this Yates calculation or just use the average of the other values in your replicate. But you had to have balanced data with the traditional AOV. And so you would fill in those missing points with that estimate. Well, with the least square estimation, now it's really running a linear model on your data. So if there's missing data, it'll just adjust that mean. So that's really what the adjusted mean option means. And then Charlotte just kind of had a confirmation question there about going through each column individually. So big picture, that's really what we want people to do is, although it seems real convenient just to have ARM look across all your data columns and give you a list, I think you're much better off looking at each data column, and it goes pretty quick. If you're worried about the amount of time you spent, today we talked through every option and every idea, but really it's pretty quick. I mean, column 13, okay, there's an AR. Well, AR is a little deep, so maybe I want to look at the graphs. Maybe not. That makes sense. That's non-parametric because this is well, yield, probably that doesn't make sense then, so I might want to look further. But it's so easy just to press next, look at that list and decide, is it all IID? Great. If not, maybe I spend a minute to look a little more into the numbers and make sure I want to do what I want. But this is IID, so that's easy. Let's just double click on that and move to the next one. So in practice, it's a lot faster, but still to get your hands on that data, again, looking at the information and not just blindly selecting everything real quickly is, I think, important. One more question here that I see, the Duncan test, and I'll admit, I think whatever test I was using is probably just by chance, to be honest. The mean comparison test here, I think we alluded to them a little bit in our first session about the selection of them. It's really in order of how liberal they are. So LSD is the most liberal, and so gives you the highest chance of a type 1, a false positive. And then down to the Tukey's HSD is the most conservative. So that one is least likely to give you a false positive. But then, of course, you have the type 2, where maybe you could potentially have a false negative as well. So that's just the order there. Duncan's, to be honest, I just probably happened to have that from maybe a report set helping somebody in the support mailbox. But I would say in general, just looking at that list, Duncan's is maybe a little more liberal than the student numericals. So the SNK, I think, is what we select by default in ARM, just because it's somewhat balanced. It's a little more on the conservative side, but it's not quite as locked down as HSD. Really, the debate about which one to use can depend on a variety of things. The penalty of failure is what we talked about in the first session. That can really help to decide the test and your alpha level. But yeah, I'll admit that really the selection there of the test I was running isn't super indicative of a hard recommendation one way or the other. Well, thanks everyone for the great questions. It's really great when we get questions. I know then people are listening, engaged, and we can answer and cover topics that matter to people. So I appreciate all the great discussion, and hopefully we'll see some of you guys next week as well. So thanks everyone.